Why can one piece of steel bend like a paperclip, while another, made from the same steel, holds a razor edge? What changed if the ingredients didn't? Here's the punchline: heat treatment doesn't magically add strength. It rearranges the steel's microstructure, the tiny crystal patterns inside the metal, so the same atoms behave like a different material. Think of it like the same bricks, but a new architecture, a cottage, a fortress, or a glass tower. Same parts. Totally different performance. Steel isn't one solid thing. It's a crowd of microscopic crystals, called grains, stitched together. And inside those grains are imperfections, grain boundaries, dislocations, and little roadblocks that decide how easily the metal can deform. When steel bends, atoms don't just slide like butter. They move along specific paths, and those paths can be blocked or freed depending on what the microstructure looks like. The biggest lever engineers pull is a phase change. When steel is heated high enough, the iron lattice shifts into a structure called austenite. In that state, carbon can dissolve more easily inside the iron lattice, like guests finally fitting comfortably in a hotel that has bigger rooms. This matters because carbon is the troublemaker that makes steel, steel. It's small, it squeezes into gaps, and it changes how the lattice can move. Now comes the key question: how do you cool it? If you cool slowly, atoms have time to diffuse, time to walk to where they want to be. That tends to form softer, more stable structures, like ferrite and perlite. The steel becomes easier to machine, easier to bend, and less likely to crack. That's why some heat treatments exist, not to make steel hard, but to make it workable and consistent, so it behaves the same across a whole batch of parts. But if you cool fast, diffusion can't keep up. Carbon gets trapped. And the lattice can't calmly rearrange into its comfortable, low-stress structure, so it snaps into a strained form called Martensite. Martensite is like freezing a messy room instantly. Everything is stuck where it landed. The structure becomes extremely hard because it's full of internal stress and obstacles that prevent atomic layers from sliding. That's great for wear resistance. It's also risky because high hardness often comes with brittleness. A super hard structure can chip or crack if you shock it the wrong way. This is where the magic is actually engineering, tempering. After creating Martensite, manufacturers often reheat the steel in a controlled way, not to melt anything, but to let the structure relax. Some of that trapped stress eases. Tiny features form that make the steel less fragile. You give up a bit of maximum hardness, and you gain a huge amount of toughness and reliability. That's why good tools and blades aren't just quenched. They're quenched and tempered because a hard edge that chips is garbage in the real world. Heat treatment also tunes grain size. Big grains can make steel behave more unpredictably and reduce toughness. Finer grains often improve strength and impact resistance because cracks have a harder time racing through a maze of boundaries. Processes like normalizing are used to reset and refine the structure, especially after welding, forging, or heavy forming, so the final part isn't hiding weak zones. And sometimes the smartest move is not hard everywhere. Engineers often want a hard surface for wear, like a gear tooth or shaft, while keeping a tougher, more ductile core that can absorb shocks. The outside resists scratching and fatigue, the inside prevents catastrophic cracking. It's the same steel, engineered into a layered job description. So heat treatment changes steel because it changes the internal architecture, phases, grain size, and trapped stress, turning the same atoms into very different behaviors. Next question: what should we break down next? Why stainless steel resists rust, or how springs store and release energy?